Hi, it's Manuel of Entagma. Today I want to make a vein grow. People did this in the past using L systems or particle systems or other techniques. Today I want to show you yet another technique. If you download the start file, you find this Kitbash vein growth object inside of it. And if you dive inside, you find this file node importing an EPS file I drew in Inkscape. This file contains three splines, sitting here somewhere in your scene. For the effect to work, these have to start at the origin, so I appended a transform to move them to the origin. But not only that, I want to orient them along the z-axis, because the z-axis is somehow a special axis. If I use matrices later on to transform these, the z-axis is the axis that the stuff points to. So I not only transformed them, but I rotated them by 90 degrees to make them point in the z direction. But that is not enough. I have to make sure that the tangent of the first segment here is oriented along the z-axis exactly. And that is why I appended these three transforms here. I used a group, and if I just input a number here, I refer to the primitive with this number. And by using these transforms, you see, I transformed all the individual splines such that they point exactly along the z-axis with their first segment. But because of these splines being drawn in 2D application, they are totally flat. And to make my vein 3D, I need at least one segment to be 3D. That's why I split this input here into two streams. On the left, I just used this one segment here by using 0 as the group, and the other blast uses 0 as the group, but delete non-selected is checked off, so it contains the other two primitives. And then I resampled this to be left with very few points and edited these to be 3D, as you can see. So this is how it started. All the points sitting in one plane, and then after the edit, it's a 3D curve. And then I appended another resample with treat polygons as subdivision curves. And by doing this, I create a smooth three-dimensional curve. To have the same resolution on all the primitives, I appended the same resample to the other side of the geometry stream, and then I merged everything. So after this treatment, I have a library composed of three splines, or three primitives, that have the same resolution, start at the origin, and are oriented along the z-axis. And one of them is three-dimensional. Great. With this in place, we can start our setup. The very first thing we have to do is to create normals on our splines. I use a wrangle for this, a point wrangle, appended here. Name it create normal. And just state at n that the normal should be a vector. And in our case, because everything is pointing along the axis, the normal should be 0, 1, 0. You can check this, and you see now everything has a normal. This normal is needed for the next node, and that is a parallel transport node that I coded in a former tutorial. I did a tutorial on parallel transport that is used to create curve framing, and instead of re-implementing this node, I just want to copy it from the old setup and use it here. So let's do that. You can download the setup, it's linked beneath the video. And from there you can just copy the parallel transport node and append it here. It will create three vectors for every point of these primitives that are orthogonal and thus create a framing for these curves. And these vectors are called PT tangent, PT normal, and PT bitangent. And to make them visible, let's create a visualizer. So the first one is PT normal, and the attribute is called PT normal 2. It's not text, but it's a vector, like so. And this is the vector PT normal. Now I can just right click here and say duplicate. And the next one is PT tangent, PT tangent, and PT tangent, and this one is blue, just to be able to distinguish between the two, like so. Here, and then let's copy this again, or duplicate it, and let's call the last one bitangent, like so. And color it green. Okay, now we have the vectors. They are a little bit long, so let's go in here and say 0.1 as length for all three visualizers, like so, and the last one 0.1. And you see the node happily creates a curve framing. So this is a system of three orthogonal vectors giving the curve an orientation. But to be useful for Houdini, three vectors are not the best thing. What we want instead is a quaternion. So let's create a VOP and let's create a quaternion from these three vectors. So let's call this node create orient, because orient is the name of the standard orientation attribute that is a quaternion, and dive inside. To create a quaternion called orient, we first have to bind the three vectors. So one bind node, and let's bind PT normal, and its type is vector. Now you can copy this by using the Alt key, and let's call the next one PT tangent, and a third one PT bitangent. Brings all the vectors in. And now we have to take a little detour. To create a quaternion, we first want to create a matrix. So let's create a vector to matrix, like so. And the bitangent is the x-axis of this matrix. Then the normal is the y-axis, and the tangent should be the z-axis. That was the wrong connection. Like so. Now that we have a 3x3 matrix, we can use a matrix to quaternion, matrix 3 to quaternion node to create a quaternion from this rotation matrix, and now we can bind it with a bind export node to be the orient attribute. So orient, and type is float4 or vector 4. Vector 4 is color-coded in this neon yellow, like so. And now we have an orient attribute. Let's check on the geometry spreadsheet. And we see here that we have an orient quaternion. So let's turn off the visualizers we just created, and instead let's turn on the orient visualizer I already created, called orient, and its style is axis, because this is a rotation. And if I do so, we get an orient attribute. And you see that this orient attribute is pretty much oriented exactly the same as the three vectors, because it's composed of the three vectors. Now we have a tidy, nice orientation for the curves, and can go on from here. What I intend to do is to use one of these three splines as a starting spline, and then choose randomly one of the three splines and append it to the end of the first spline, and do this over and over again to form a long vein that winds through 3D space. So how can we do this? Well, first create a blast. And let's put in 2 into the group field, and check delete none selected, which gives us one of these three splines, the third one, primitive number 3. Great. Now let's create a VOP, a point VOP. And we want to append another one of these splines to this spline. So let's create a second blast, and let's use 1 instead of 2 here, so another 1. And this one is the one we want to transform. So this goes into the very first input of the point VOP. And this one here is used as reference because we want to transform that one to the end of this one. So this goes into the second port of the point VOP. And let's call this transform branches. Make it visible. Now dive inside. To be able to transform this geometry to the end of the other one, we need information about the other one. We need the last point of the other one, and we need the last orientation of the second spline. And we can get both by using a primuv node. So create a primuv, called primitive attribute inside of VOPs. Looks like this. And you can specify a u value along the curve to sample an attribute. So first connect the second input to the file port because we want to read from the second input. And then we want to create a constant. And this constant is of type vector, just because the primuv node uses a vector as uv coordinates, because it not only works on splines, but it works on all primitives, even Bezier patches or NURBS patches. That's why this value here is three-dimensional. So connect it here, and just state 1 in the very first field, because that is u. And 1 means the very end of the primitive, so the last position. And then click the primuv and change the attribute it should sample from CD, which is standard, to P. So now this gives us the position. And to move this geometry to the end of the other one, we just add this position to the position of all the points, like so. If we do that, this one jumps over. If we go up one level and make the other one visible by templating it, you see that the geometry jumped to the very last point of our second primitive. That is good. But it does not stop here. This is position, but we need orientation too. So let's import the orient attribute of the second spline. So duplicate the primuv node. We can keep the connections because it uses the second input regarding geometry, and it uses the u value of 1. But it samples the attribute orient. And that is not a vector attribute, but a vector 4 attribute. So now we have an orient attribute. To rotate the points, I love to use matrices. So I convert this quaternion back to a matrix by using the quaternion to matrix node. Quaternion to matrix 3. By doing this, I recreate my matrix 3 from the orient quaternion. And now I can use this matrix to rotate all the points. And that is done by using a multiply. And I use my input points and multiply them by the matrix. Now they are rotated. And instead of adding the standard points to this add here, I now add the rotated points to my add. That was the wrong connection. I want to add the last point of this primitive and then all the rotated points to it. And now you see that I have rotated the geometry to fit the last rotation of this segment here and moved it to be exactly in this place. So I moved the entire thing to the last point of the other segment. Now let's create one spline from both. To do this, we need a merge node, and we merge our first geometry and then our transformed geometry. Now we have one geometry composed of two primitives. If you click on primitive numbers, you see you have two primitives. But we want one primitive. To do this, we can use a join operation. So append a join operation, and as soon as I do this, I am left with one primitive, because now both primitives are joined to form one primitive. And if I click on orient, you see the orient is not valid anymore. These tangent lines here deviate from the spline, and that is due to the fact that the orient attribute was not rotated with the points. We could rotate all these vectors, or we can just run the parallel transport again on the newly created spline. And I think that is a better idea. But before we do this, let's fuse the points. And now let's run parallel transport and create orient again to do a new curve framing on the newly created spline. We don't need to create normal because the normals are still present on our geometry. So duplicate these two nodes and append them here. And after this operation, we now have a new beautiful curve framing on the curve. So now we created a more complex spline out of two spline segments from the library. But to create a long vein, we have to do this over and over again. So we, instead of using blast nodes and doing everything by hand, should use a for loop. So let's create a for loop and do this iteratively. Create a for loop. For loop with feedback. This gives you a block begin and a block end node. Everything between these two nodes is repeated as many times as you state on the repeat end. At the moment, its iterations are set to 10. So now, the first thing we want to have inside of our loop is the transform branches. We want to start with this blast here. That is our very first segment, and this should go into the loop. And now we want to merge the stuff that comes out of the repeat begin inside of the loop into this merge node. So cut this connection and instead connect this here. As soon as I do that, everything beneath this node is part of the loop. And that is indicated by this convex hull that is drawn around all these nodes. Switch the connections to make this connection the first one and move this stuff over. And here is a transform branches that uses this second primitive here. And the transform branches needs to use the input from the loop as reference instead of that one, because it should be part of the loop. That one here can stay the same for now, because it's just referring to the second primitive we want to append. And now we append this to the repeat end and make the loop visible. And we get this. If we click on the visualizer for the orient attribute, you see we have a now quite complex curve. And this complex curve has a nice curve framing. So what happened here? Well, 10 times this primitive here is appended and appended and appended and appended to the end of the spline that is created. So it starts with this primitive, then appends 10 times this primitive to the end and creates a new spline with new curve framing. And the result is this nice looking, interesting spline. But it's not perfect yet, because at the moment it's always appending the same primitive. And that is this primitive here. Instead, we want to choose the primitive to append randomly. So we have to write an expression that makes this blast choose a random primitive. How can we do this? Well, we have to first create a random value. And we can base this random value on the iteration, because in every iteration of the loop, we want to use a different primitive. To get hold of the iteration, what we can do is we can go to this repeat begin node and create a meta import node. That looks like this. It's a second import node. And this node generates information about the loop. It does not interact with geometry, although it's the input node, but instead it creates meta information, and it creates this information as detail attributes. So if you go to the detail tab and select this node, you see that these 4 detail attributes are created by this node: the iteration, the I value, the num iterations, and the value. And the iteration is the current iteration, and it is the value that we want to use for our random function. Now that we have this, we can write an Hscript expression that makes this blast choose a random primitive. So let's go to this blast node, and in this group field, press Alt-E to open the expression editor, because this is quite a long expression, and it's easier to write it in this editor. The very first thing that we have to do here is to insert backticks, because this is a string field. and a string field does not execute expressions because it thinks it's just a string. So to tell it to execute what I write here, I have to use backticks. So just create 2 backticks, like so, and write everything between these backticks. The very first thing we want to have is the iteration value. And this is a detail attribute of the repeat begin, 1 metadata 1 node. So let's use a detail function to get this value. So detail. And then we have to specify the node path of the node we want to use, or from which we want to read the value. And that is 1 level up, and then repeat begin 1 metadata 1 slash like so. And the next value is the name of the attribute we want to read, and this is iteration. And then it's the field of the attribute value if the attribute has more fields, like a vector, for example. In our case, it's 0. So that is the detail value. That is the iteration value that we have now. Press apply and accept, and let's see what this gives us. And you see it's a very short spline. And that is due to the fact that this iteration value goes from 0 to 10. That means as long as this evaluates to 0, 1, or 2, it's valid, because the BLAST can choose between 3 primitives. But after that, it's not valid anymore, and it does not find a primitive, and thus it does not return any geometry. And that is why we only append 3 geometries here: the first, the second, and the third. So we somehow have to go in here, press Alt-E again, and transform this value to always be in the range between 0 and 2. So let's do this. So first we want to create a random value from this iteration value, so include everything in a rand function. Rand function uses the value you provided with as a seed and then generate the value between 0 and 1. So now we have a value between 0 and 1. Now we want to floor this value and then multiply it by 3.0. So we take this value between 0 and 1 and multiply it by 3. That means if the value is 0, it stays 0, but if it is 1, it is 3. And then we floor it. That means we get rid of all the decimals and just keep the integer part of it. And to convert it to an integer, because we need an integer here, we put everything inside of an integer function. So that is quite a mouthful. Let's go through it again. First, with a detail function, we grab the iteration value from the metadata node. This iteration value is running between 0 and 9 at the moment because we have 10 iterations set on the loop. Then we create a random value from this seed value, which is between 0 and 1, and multiply it by 3, such that we have values between 0 and 3. Then we floor this to just keep the integer part, and then we convert it to an integer. So let's see if this works, and if we do so, yeah, it seems to work. Now it chooses a random spline in every iteration and appends it to the previous spline, creating a nice complex spline in the process. And to be able to specify a random seed, we can add one more component to this here, to this expression here, and that is a random seed that we can just add to the iteration value. So let's just add a random number here, like so, and this number can be used to generate different seeds. And this loop generates an intricate spline from the library of splines. Although I only have 3 splines here, the resulting curve is very complex, and you can imagine if you use more splines, it gets even more complex. But still, you can influence the look of this by specifying the look of the elements. So that is a quite nice technique to generate a procedural curve. If I now go to the repeat end and up the iterations, say to 100, like so, you see that I now can create very, very intricate splines with this loop, because it always appends another spline to the end of my vein and thus creates a more and more complex vein. To make the result even more interesting, let's add one more component to our transform branches swap. Before I do that, let's go back to 10 iterations to make this stuff execute faster. I want to add random rotation to the individual segments. So whenever a new segment is appended, it should rotate randomly around its local z-axis. So go into the transform branches. That is what we had here. Let's clean up a little bit. Move this over, and we want a random value and then generate a rotation from this random value. So start with a parameter node. Parameter, and let's call this rand rot, like so. And then we want to use a random function to generate a random value from this rand rot. And the rand rot should be the rand rot parameter should be an integer, and this integer generates a random value. Now I want to fit this random value because it should resemble a rotation, and a rotation usually is specified in radians. So this random node generates values between 0 and 1, but I need values between 0 and 2 pi. So we use $pi, which is an inbuilt constant, times 2 here, and that will fit our values to be in the range between 0 and 2 pi. Now, I need a rotation around the local z-axis, and that can be done by using one of the vectors of this rotation matrix that we created earlier. So by using a matrix to vector, matrix 3 to vector, I can split my matrix in 3 vectors, and we want to use the z-axis to create a new rotation. And that can be done by using a quaternion node, because a quaternion is specified by an axis that the rotation should happen around and an angle. And the angle should be our random value, and the axis should be the local z-axis, so the z-axis of this matrix here, which gives us a new quaternion. And we can, again, use a quaternion to matrix to convert this quaternion to matrix form. And now I can just multiply this rotation by another rotation matrix, like so. And you see everything looks different now. And that is due to the fact that a second rotation is applied whenever a new primitive is appended. And if I go up and choose another value for this rand rotation, every piece is rotated differently with a random value. But at the moment, it's not random per segment, because this value is global. We have to alter this value for every iteration. So another Hscript expression is needed. But in this case, the iteration value itself should be enough. And because this is not a string field, we don't need backticks here. So just type detail, and then the path to the node that holds the detail attribute, which is the repeat, begin metadata1, like so. And then the name of the attribute is iteration, and the field is 0, like so. And if we accept this, now every iteration uses a different random value to add an additional orientation or additional rotation around the z-axis to this curve, which makes the curve look far more interesting. And if I go now up with the iterations to, let's say, 30, I have a very interesting curve. And I can generate as many different variations of this curve as I like by just going in here and changing our random seed value. Let's say do this, and we get a totally different curve composed of the same elements. So this is somehow a fractal technique because it uses the individual elements to compose something more complex from it. But it's very nice because it generates curves of arbitrary length that have a certain feeling to them because they are based on the library. And that concludes part 1 of this tutorial. In the next part, I will show you how to add branches and thickness and geometry to this vein and how to make it grow. So thanks a lot for your attention with part 1 and stay tuned for part 2. Let me say a very big thank you to all our patrons, especially Mohammed Al-Abri, Mikhail Ivanov, Rob Bryant Jr., Rafik Anadol, Chris Hebert, Nick, John Kunz and Joseph Howard. Thank you so much.